Hello and welcome to this video on how to run a Monte Carlo simulation study in Mplus based on an existing analysis. My name is Geiser. On this channel I present weekly statistics tutorials typically related to structural equation models, latent class models, or other multivariate statistical models, and often related to the Mplus software. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to leave a comment in the comment section, and also to check out the description for additional videos and free workshops. So in this video, I want to show you how you can run a Monte Carlo simulation study in Mplus from an existing model or from an existing analysis, thus simplifying your specification of the population parameter values for a Monte Carlo simulation study. Oftentimes in practice, researchers who plan a statistical analysis or study have the question of what sample size will be sufficient for their analysis. So they want to know how many individuals do I need so that my structural equation model, for example, will run properly. And we know that structural equation models and latent class models and other types of models are large sample types of analyses, so you can't typically run those with just 30 cases. You have to have a substantial number of cases, but also you want to make sure that you don't sample more than you need necessarily, or many more than you need, because it can be costly to collect data from thousands of people. And so in this case, for example, I ran a two-factor confirmatory factor analysis model based on an existing sample, and you can see here the sample size was 552 cases, so it was a pretty substantial sample size. And so one question that I could have could be, well, could I not do this with fewer people? So would it still be okay if I did this with just 100 cases, for example, or 200 cases? Would I still get reliable results? Would I get unbiased parameter estimates? Would I get reliable fit statistics? Would I get unbiased standard errors for the parameter estimates? And would I have sufficient statistical power for the parameters that I want to test for statistical significance? And so all these things can be examined by running a Monte Carlo simulation study, where we simulate our model under different conditions, for example, different sample size conditions, and then we can take a look at whether the parameter estimates, for example, for a smaller sample still come out as unbiased, whether the standard errors come out as unbiased, whether we approximate the chi-square distribution well for model fit testing, and we can also look at whether we have sufficient statistical power. And so one thing that is very practical in the Mplus software is that you can simplify a simulation study when you already have a model that you have analyzed for a real data or an actual data set, because then Mplus allows you to save the parameter values that were estimated for your data as values, or to save them to an external file, and then you can import that file into a simulation study, so to say, and then you don't have to sit there and figure out, oh, what parameters should I assign to each of the factors, for example, in my simulation, which can be tedious to come up with all the factor variances, error variances, loadings, and so on. And so in this scenario, then you're using the values from a real application, and you know that these are plausible because those are the ones that you found, so say for actual data. And so that can be helpful when you run a simulation from previous analysis. Then you already, so say, have parameter values that are at least not totally implausible because they were found for actual data, and you don't have to come up with your own, so to say. You just use what you have, and it's very quick to do that. So that's what I want to show you here. So here I have my input file for a two-factor confirmatory factor analysis model, and you can see here there are 4 indicators for the first factor, so that would be a math performance factor, and then there are 2 indicators for a second factor. Those indicators measure spatial abilities. MRT here stands for mental rotations test, so those are indicators of a spatial abilities test. And so this two-factor model looks at the structure of the math test and the spatial ability test, and then one key thing of interest is whether the two factors are correlated. So is there a relationship between spatial abilities and math performance, and that can be estimated as part of the model. And so one question, for example, could be here for the simulation study could be, is the power still sufficient when I reduce the sample size to show that this correlation is significantly different from 0? With 552 cases, I can show you here we have enough power to show that this correlation is significant, but maybe in the future we would like to go with fewer people, and we want to see whether we still have enough power when we use a smaller sample. And so what we do here now in this Mplus input file, what you don't usually do when you run Mplus, is I added the save data command and requested that the estimates from the model be saved into an external file that's called est.dat. So I chose the name for that file. And what Mplus will do now is it'll export the unstandardized parameter estimates from this model to this file est.dat. And then you can use those estimates directly in your simulation when you do a Monte Carlo simulation. So let's real quick take a look at the output here for this model. And so I want to show you, so it fits well, so that's good. Chi-square is not significant. And then here you can see that the covariance between the two factors f1 and f2 is positive, and it's significant. You can see the p-value is very, very small. So obviously with a sample of 552, we had enough statistical power to show that these two factors are significantly correlated. When we go to the standardized solution, we can see what the actual correlation is. Above in the unstandardized solution, we get the covariance. Here we get the correlation in the standardized STDYX solution. So this here is the correlation 0.335. So they are moderately highly correlated. And again, this correlation is statistically significant. So now again, we might want to be interested, or we might be interested in finding out whether this correlation is still or whether we still have enough statistical power to show that this correlation is different from 0 when we reduce the sample size. And so we can do that with a simulation. Now let me first of all show what happened here by introducing this save data command. You can see that at the bottom we get save data information estimates and the name of the file, and the fact that the format in which the estimates were saved was a free format. And so now we can take a look at that file. It'll be saved to the same directory where you have your input file and your actual data file, and then you can open it in Mplus. So here I already opened it. It's called est.dat. And so you can see here that all the estimates are in this file. Let me make this a little smaller so you can see it better. So here you can see all the estimates from our model are there in a particular order that Mplus knows, so to say. Mplus has a particular way of saving all those estimates to the file. And so then these can be imported into a simulation study of the same model. And that's what I want to show you next. So let me open the input file for the simulation that I already prepared. And so here you can see that in the simulation, I was trying to find out whether the model is still okay to run with a really, really small sample of n equals 50. Now this is an extreme kind of condition that I chose here for illustration, so that you can see actually that it doesn't work, that we shouldn't do that, and why it doesn't work. And so this is a really small sample that is only 1/10 or smaller than 1/10 of the original sample of 552. So we're simulating this model now for n equals 50. I have the names of my variables here in the Monte Carlo command. I specified the sample size for each replication of the simulation to be n equals 50, and I'm using 1000 replications. So now Mplus will draw 1000 samples from the population model and estimate the model in each of those samples of size 50, and then give me a summary of the estimated parameters, fit statistics, standard errors, and also of power. The population values are drawn, are taken out of this data set est.dat. So that is the thing that is specific here. to specify population equals std.dat, which means that rather than manually specifying the parameter values for each replication of the simulation, we are now taking those estimates out of our est.dat file. And that makes it really practical, because this allows us to then not specify all the parameter values manually, which would be a lot of work. So then these are also used for calculating coverage, so for making sure that the confidence intervals are appropriate as well. The model population command then, or in the model population command, where we specify the population model for our simulation, we simply have to specify, or we can copy and paste the same commands from our actual data analysis for the two-factor model. We don't have to include parameter values for each parameter like we would normally have to do when we do a simulation study, because those parameter values are automatically taken out of the stat file, and Mplus knows the proper order of those, because the model itself was also run in Mplus, and so we don't have to worry about the order of the parameter values or anything like that. Mplus will automatically assign the right parameter values to all free parameters and fixed parameters of this model based on this dat file here. The model that is then fit to each sample is specified here under model, and it's the exact same model, so we're using a correctly specified model in our analysis. And then finally we specify output tech9 to see if there are any error messages, if there are any replications that come out as improper, for example, or as non-converged or something like that. So let's take a look at the output a little bit here. You can see input reading terminated normally, that's good, but then a bunch of other things went wrong. So you can see here number of observations was 50, so a really small sample for a confirmatory factor analysis model. And you can see that not all of the requested 1000 replications actually did converge here. Only 958 did converge, so about 5% of replications were non-converged, so that's not so good. So it's a relatively high rate of non-convergence due to the small sample. So that's one thing that is noteworthy here, that not all of them worked. And then when we scroll down a little bit, we can take a look at some of the output. For example, the chi-square distribution approximation here. You can see that the approximation of the theoretical chi-square distribution was not very good. The expected proportions are given here in the leftmost column. So those are based on the theoretical chi-square distribution, and on the under the observed column here, you can see what proportions were actually observed. And so for a common rejection rate of 0.05, where we would typically reject a model if the p-value of the chi-square was 0.05 or smaller, you can see that the actual rejection rate was 0.079, so about 0.08. So we would reject more models than we should, so to say. So we have a slightly inflated type 1 error rate. We would reject the null hypothesis more often than we should, and so we would, so say, reject too many correctly specified models in this case. So that's a problem with a small sample. When we use a chi-square test of model fit, the sample obviously is too small to get a reliable chi-square test of model fit p-value for that, and you would risk rejecting too many models that are actually okay. And so let's take a look at the parameter estimates real quick as well. You can see that the actual population value that was drawn from the est.dat file is given here in the population column. So those are the values that are in this dat file. And then the average estimates are given in the next column here under average. And so you can compare those two columns for a given parameter to see if there was any parameter bias. And you can see for the loadings here for factor 1, it's relatively good. So there's a relatively good match here between the population column and the average estimate column. So that shows you that there's little bias, even with a sample size of 50. But there is some bias for some parameter values, like for example, the loading of the second variable on the second factor, the population value was 0.92 and the average estimate was 1.16, so that is a bit off. So that's a substantial amount of bias there for this loading. These should be closer, so that's not good. And then also the covariance between the two factors was overestimated a bit on average, so this is higher than what the true population covariance was. So there is some parameter bias due to the small sample. But what is worse is the standard error bias. You can see here, for example, for that loading we get a substantial discrepancy between the Monte Carlo standard deviation of this parameter across the 1000 replications, which was 1.35, and the average standard error, which was 2.8576. So this is a huge discrepancy here between this number and this number, showing you that there was substantial standard error bias. So the standard errors cannot be adequately estimated, at least for some parameters in this model, given the sample size of 50. Now for others it's okay. You can see here this looks okay, this looks pretty good, this looks pretty good, but for this loading it does not look good. For the covariance it looks okay, but the covariance itself is pretty biased, so we wouldn't want that. And then also the factor variance of the second factor, you can see, is not looking good, both in terms of parameter bias as shown here, and then also in terms of standard error bias. So that's not good at all. So this alone may lead us to conclude that 50 is not enough for this model, sample size of 50. And there are other things too, like for example, when you look at the residual variances, there's a lot of bias here for at least some of the indicators where the population value does not line up well with the average estimate. Also, we can look at the technical 9 output at the bottom, where we can see any error messages, and here you can see that there were many error messages. So the first replication didn't at all converge, so there was a problem of non-convergence for replication number 1. Replication number 2 had a warning about a non-positive definite residual covariance matrix theta. This typically indicates a negative residual variance estimate, where you have a negative error variance for one or more indicators, and that was also the case in replication 5, replication 6, replication 9. So you can see there are 10, 14, so many replications had improper solutions. And so this also is typical. When you have sample sizes that are too small, you get more improper solutions, you get more standard error bias, and that is not something that we want. And then one thing that I also wanted to show you is power. So when you go to your parameter estimates again in the simulation, the last column here in the simulation output, percent sig coef, this means the percentage of or proportion of replications in which the parameter was found to be significant at the 0.05 level. And so this is an empirical estimate of power, what you get here. And so one parameter in particular for which we would like to know power is the correlation or covariance between the two factors. And so we saw in our actual application with 552 cases that this covariance was statistically highly significant. The correlation was about around 0.3, and so this was significant. But here you can see that power with a sample size of only 50 is very low, 0.383. Typically we want power to be close to 1, so ideally very close to 1. Some people say it should at least be larger than 0.8. Some say it should be greater 0.95. But definitely larger than 0.383. So this shows you that power for this covariance is insufficient also with a sample size of just 50 cases. And I'm sorry, you actually couldn't see this because it was outside of the frame. So here you can see it. Let's go over to the side. Here you can see percent significant coefficient. This is the last column, and so here is the power value for this covariance, and this is something that is insufficient. So I hope you found this video useful to see how you can run a simulation study in Mplus from an existing model. It's very straightforward. You just simply save the parameter estimates, you import them into your simulation, and then you can run the simulation for different sample sizes or for other conditions. I hope you found this useful. If you did, then please don't forget to subscribe to this channel and to hit the like button. Also check out the description for additional resources, and I'll see you next time.